Oh, 40 minutes gone out the drain, guys. Welcome back to Jogamin. I recorded a 40-minute video. I'm on a MacBook, and OBS decided to freeze the screen. So, we're gonna learn about integrals or antiderivative. They're the same word. They're the same thing. Okay, so it should be a lot shorter than my original, so let's get with it. Antiderivative is antiderivative. I need to check if I'm still recording. Okay. Wait. Yeah. Okay, so antiderivative. Oh crap. Antiderivative. It has anti in it. It has derivative in it. What that means is that the derivative of an antiderivative equals the derivative, or the original function. Yeah. Like in this illustration, I get the derivative of big F. The antiderivative is denoted by big F. F of x equals small lowercase of x. But realistically, in a lot of cases, I'm gonna write something new. Never seen before. If you got the antiderivative, I mean, if the antiderivative equals this, then the derivative, or the derivative of the antiderivative would just be f prime x. And then the derivative of that, the antiderivative of that is just f of x. So it just goes down. So antiderivatives make the little dashes on the top of the function go downwards. Okay? They go down. And in many ways, antiderivatives are like the opposite, like direct opposite of a derivative. At times, they're kind of similar. And and the reason why they're similar is because of how you get to one another. So let's scroll down. So let's say f of x equals 2x. Now, the antiderivative would be x squared plus a constant of integration, which means that because you get a derivative of a constant equals 0, there's a possibility that there is, when you get you should get back to the function you derived from, right? So that's why this right here should have a constant, because you never know. Yeah, and I hope you can see how x squared and 2x are related in the way that 2x equals someone's derivative, dy dx. It's some function's derivative, right? And we know by power rule that we have to put down the power here and then decrease it by 1, right? Well, since there's already a 2 here, that would imply that the antiderivative not only added to the power, but also divided by 2 to get back to the original function. So basically, where did I write it somewhere? Basically, yes, over here. X to the n plus 1 over n plus 1 is the power rule's antiderivative. The antiderivative of power rule. And notice how, compare and contrast, x to the n minus 1, n to the x. Notice how these two are the opposite, like literally. This one's dividing and plus 1. This one is plus 1 on the end. This is the minus 1 on the end.
Not maxing out credit cards? That's
So, yeah.
what I'm talking about. Learning what credit utilization is.
The reason why there's an n plus 1 down here
credit.
because remember we minus 1 and then we put it, then we put the original n there. And since now our now n is the n minus, we have to get to the n plus 1. So with my example of x to the 5, its derivative would be 5x to the 4th.
We know progress looks different for
The
everyone.
current n, the original
For some,
n
it's a new
was,
heart.
let's denote that as
To others,
n1
it's
equals
access
5,
to one of our many
and
groundbreaking
2 now
clinical
equals
trials.
4.
And sometimes it's
So
simply the joy
n
of hearing
plus
your baby's
1
heartbeat for the first
and
time.
2 plus 1 equals 5.
That's
So
why
x
you
to the
can
5.
find Cedars-Sinai locations
And
with the
n,
best doctors
this should be a
across
5
Los
here too.
Angeles.
Like
Because
if
your
this
progress is our
was,
progress. Visit your nearby
should be like
Cedars-Sinai
n
today.
minus 1. What? What? You can't do this to me. Alright, buddy. They canceled me out. Alright, whatever. So, yeah, it should be an n minus, or just be n on here. But like, in general, without an n here, you'd probably n plus 1, n plus 1. So, you go back. I can't really specifically show now, but okay, so f of x, this is where we get the real notation. F of x, the antiderivative f of x, equals the s sign, a giant S, of f of x dx, where you get, where dx is a very small distance between x that is infinitesimally small, close to 0 small in fact, and that way we get it is getting the derivative equals f prime x, right? So this is a fraction. You could multiply dx on the other side. So when you do that, you get f of x dx equals dy, and if you get the integral of it or the antiderivative of it, you just get y equals f of x. Right. Yeah, it just boom. Then let's get to example of why. Wait, oh yeah, hold on. I labeled some stuff here. So this whole thing is the integral, and this function inside is called the integrand. And when you get the derivative of an integral, you should only get the integrand, like as I showed earlier. If replace f of x, this giant f of x with this, the derivative of that should be the inside, this one right here. Yes. See, I'm still recording. Yes. Okay. Next. Graphically, this is what an integral is. The area under the curve. Graphically, it is this. If it was y equals x, where the width of the circle, the width of the what do you call it? The width of each square for the Riemann series, and you know what Riemann series right here, the n to the whatever times, you know. So this is the Riemann series, but instead of changing x, which is the width of the squares that you're making, instead of them being like 1 squares of 1 or 1/2, whatever, you're gonna make it infinitely so small that they're literally like the exact value of f of n, and you just do it all the way up to your limit or your bound, your interval bound. So this is what an integral is, the Riemann series version. So limit as n approaches infinity, where n is the upper bound, I equals 1, f of xi times change in x, where xi are specific values that I'm pretty sure is b minus a over n. Xi or not, wait, xi or I think xi equals b minus a over n. and change in x is it should be changed in xi, where they're so small, like so small in distance. So it's probably, yeah, so this change in x would be dx, where the change in x, like how, as in change in y over change in x, as in subform theorem, the change in x is so small that it's literally the function, like the literal value of the function times like very small stuff. It's hard to explain this without being able to draw, but yeah. And then look at here, the rectangle dx f of x, and since this is a triangle shape, you would get f of x dx over 2, which, if you remember from here, x to the n, well, x right now is 1, 1 plus 1 is 2, n, which is 1, plus 1 is 2, so x squared over 2. Ooh. Yes. That is that. Yes. Okay, so for this graph here, again, it's y equals x. And notice this thing here. So remember earlier I wrote limit n to the infinity xi and stuff? Well, wouldn't that imply that if I had n to the 1, if n was 1, I would, like, it's like adding on to each other, you know? Like, this limit becomes like like a summation of summations, you know, like, because n isn't infinity, it doesn't start infinity, it approaches infinity. So if n was 1, you have the 1 upper bound of x1 times x change in x, and then if it was 2, it'd be that same thing that I just previously had for 1 plus the second bound, and for 3 it'd be you see how it's adding on every time limit of n approaches infinity? The last sequence was that minus 1. So for that reason, the way you get the area under the curve is like this. So look at this triangle. Look at this. So let's say, alright, here, we start at 0. Limit bound from a to a is 0, like how I wrote it here, from 0 to 3, alright? And then we go to 1, so 1 times 1 divided by 2 equals 1/2, which I wrote here. And then from here, 2 to 2, that's 2 times 2 over 2, that's 2 squared over 2. From 0 to 1, now it's 0 to 2. Notice how we're adding on from each other, like how I wrote in this place. We just keep adding on the area, even if it intersects from the previous area. And as we keep doing that, we'll form a pattern, which is 0 plus 1 plus 2 squared plus 3 squared plus 4 squared. You see that? And if you remember, I told you the derivative, the antiderivative of this, the integral of this, was x squared over 2. And doesn't that make sense? 1 squared, 2 squared. So basically the antiderivative is an equation to describe the change in values that you're given from the area. Okay. because I want to add one more thing. So like, if you gain the area of 3, it must be length 3, and then it has to be height 3, right? So I'm saying that it adds on because it intersects from 1 and 2. So it's basically adding on from 1 and 2, the area of 1 and 2, and then getting the area, the small square area that's not a triangle, to 3, to form a bigger triangle at 3. I hope you understand what I'm saying. It's kind of confusing, but because I can't really show you, but yeah. And then from here, this is the graph of x squared over 2 with y equals x, as you can see. And I wanted to showcase in this one that how it's very similar to its description of a derivative, and how, let's say we got the derivative of x squared over 2, right? Notice this is the limit definition. Notice how if you put in 1, you'd get back 1 in a calculator, or something close to 1. You put in 2, put in that calculator, you get something 2. So notice how these values jump by 1 every sequence, which shows that the derivative should be x, because only x, the function x, goes up by 1, 2, 3, and so on and so forth. That's how you describe the pattern. And just like this, how we saw 0, 1 half, 2 squared over 2, 3 squared over 2, and then 4 squared over 2. That's how you got the equation here. That's how you get an individual's graphics, like graphical derivative, antiderivative. But in general, the rule for any power series should be this.
Find out what's on sale in our weekly app.
Alright,
shop the deals online or in store. Sincerely Food.
Alright, so
Sincerely Albertsons.
we have the integral 3 to the x dx. What is the antiderivative? Well, remember that d over dx, du to the x is ln u to the ux. I mean, yeah, u to the x. And if you keep deriving it, this is the general rule for the derivatives of u to the x. If you keep deriving it, it's just ln u to the u times n times ux, right? So there's nothing more adding onto the function u to the x other than a constant. Keep multiplying each other. The same constant keeps multiplying over and over again every time, right? So therefore, using that logic, the antiderivative of u to the x should be u to the x ln u. So in this case, the antiderivative of 3 to the x is 3 to the x over ln 3, and you can prove this by getting the derivative, where the derivative of 3 to the x is 3 to the x times ln 3, and that cancels out with the for the denominator. You get back 3 to the x, you know? Okay, so I want to talk to you about trig. How much time has I spent? Okay. Big chungus. Okay, so sec squared x. You could prove that it's tan x without using logic, like straight integrals and stuff, because I haven't showed you how to solve stuff with integrals yet. Not really. Wait, let me see if I have. Yeah, I don't think I have. I think I have to show it. I show it later. Okay. So with only logic, we know that the only derivative that can get you sec squared is tan x. So therefore, it's tan x plus c. And the reason why I wrote bounds of these little bounds on the integral this time is to talk to you about asymptotes. So when solving an integral, you must get the antiderivative and then it's the antiderivative of the upper bound minus antiderivative of the lower bound. That is how you get that's how you get the antiderivative. I mean, that's how you get the area on the curve, right? Like you get the antiderivative, and we don't know what c is, so not now. Actually, no, you put plus c after you do this step, by the way. After you do FB minus FA, that's when you do the end. That's when you get plus C. But yeah, so in between getting from here to here, you have to do this, and you have to write the lower bound on the bottom on this little line. 3 pi over 4. 3 pi over 4 is the B, and pi over 4 is the A. And if you know your trig, you would assume it's -2 based off straight values. But the thing is, there is an asymptote between those values. Pi over 4 and 3 pi over 4 have a distance between each other, and that distance is an asymptote at pi over 2. And because of the asymptote at pi over 2, I write it here somewhere. Wait, no, I don't. I'm gonna just, because of pi over 2 equals infinity, you cannot add infinity to your thingy. So therefore, the area between pi over 4 and 3 pi over 4 is undefined or slash infinity. Which, I mean, you can't really do much after that. There's not much to say. You just know that infinite area in a closed interval means a asymptote. And with the example of big f of x equals 1 over x, we know there's asymptote at 0, right? Vertical asymptote at 0. The fact is that you cannot, like, okay, so the reason why you're minusing these is to get, let me just show you on, like, I don't think I can show you actually right now. But let's say you're on Desmos, you graph something, and you see the area on the curve, like over here, right? There's area in, like, highlighted, it's like area, right? So, what was I gonna say? Victory Royale today. You don't even know what I was about to say. Oh yeah, why f of b minus f of a is the answer is because you have to get that point, like the entire area from f of b, but you have a bound that is typically not, usually 0 would just be 0, right? So if it was 0, then you just get f of b and that's your answer. But since there's something not 0, you gotta get the area. I remember I talked about how it's the area added on and on and on. So you must subtract that earlier area. Like, let's get 1 and 3, right? I had to subtract 1, the area of 1, from 3 to only get the area from at 3, right? But then that would also include the area of giant F2, right? Which would mean that if there was an asymptote at 2, which a vertical one that went to infinity, in between those two, I have infinity, which you cannot find a definite area for it. That's why you cannot get an area past an asymptote for any function that has an asymptote. So, like, for example, if you wrote like -2 and -1 for this 1 over x, you get -1 minus 1 over 1/2, which equals -1/2. So you can get the left side, because functions go left to right, right? So you can get the left side of 1 over x up until 0, or up until less than 0, not equal to 0, right? And as I write here, like -1 to 0 minus 1 to 0, that's literally in 2 different infinities are negative and positive. They don't cancel out, by the way. Can't subtract or add infinities. Even if it seems like they're both the same infinity, you can't get rid of them. So therefore, it's just undefined past 0. If you try to get the area under 1 over x past 0, you just can't. Unless your bound started from like 1, and possibly if your bound was like 1 to 100, maybe. In fact, let's go test this. Let's hope I'm recording right now. 1 over x. Okay. And then I write t of x. Actually, no. I meant. Wait, yes, I meant that. Okay. 0 to 1 f of x dx. Oh wait, I have to make this t because the variables on this top cannot be equal. Notice how I'm trying to let's make that t instead. Notice how I can't do 0 to t in the function. But what if I did -1? Now it works. But notice how it stops when it approaches 0. It doesn't even load after this. So you see, I can get it from the negative side, but after that, it doesn't work. I don't even know what this is, but you know. Anyways, can I get from 100? Yeah, you can get it from. Yeah, retract my statement about you can only get the left side. You just can't get it at 0 exactly. And I don't even know what this is. Alright. Also, if you want the graph of it, you have the bound has to be the variable here and here, but it cannot be the variable here and here. Okay. Or that's what they want you to know, but it's really not. I'm a sheep. I'm a sheep. I'm a sheep. I'm a sheep. Oh yeah, in my example, I made f of x equals 1 over x. So this should be 1 over x. Let's just find out how to get 1 over x as the antiderivative. Well, since this is just x to the -1, you can still apply.
So, you know how to beep beep like a sheep, I see.
I do.
But is that all you can do?
Oh, you just get the derivative. My god, guys. You just get the derivative. Watch this. Yeah, look at that. Look at me. Just look at that, bro. Yeah, just look at that. It's now you can do it. Yeah, look at that. You can do it after that. You have 2 sums, but they can never be at 0. So if I ever were to write t to negative t, that would straight up just be undefined. There would be no graph because it could not get past. Oops! It literally could not get past this point. It just couldn't. There's infinite. It'd just be a graph in infinity right now.
Fall flavors have arrived,
But
and it's
you
time to
can
stock up and save.
get close.
Visit
I mean,
your
if you
local
put 0,
Albertsons
1,
and take a bite
nope.
out of fresh savings on all your seasonal
Negative
favorites.
1, nope.
From apple
See
cider
how
to
it
pumpkin
negative
everything,
1 to 1,
come savor
the
the
ace of
flavors of
is
fall.
in between.
Looking for
You
a
just
quick
can't get.
weeknight meal? Shop
I
ready to
can
eat
get
soups and whole roasted chicken, all in one easy trip. Find
Negative
out what's
2
on
and
sale
1.
in our weekly
Oh,
ads.
oops.
Shop the deals online
Wait.
or in store. Sincerely Food.
Yeah,
Sincerely
the value would be
Albertsons.
whatever this is, 0.5. Yeah, that was right.
With T-Mobile, you can get tons of benefits and still save because nobody likes having to choose. It's like being outdoors.
Yeah, so
and
basically
indoors.
that's all. That's
Nothing
oh,
like
I
the
want to
great
do
outdoors.
10 or 6
Except
squared.
heading inside to watch a movie.
6
Or like being
squared
healthy
X.
and indulgent.
Ooh, I'd like a kale smoothie.
All right.
And a fudge brownie.
See how much you can save versus AT&T and Verizon
Oops.
with our
Okay,
savings
so,
calculator at
like earlier-
T-Mobile.com/switch. Plus, new and existing customers can get the Samsung Galaxy S24 on us.
0 to t. Yeah, so like earlier, as you can see, only one strip of 10x appeared when 10x supposed to be a periodic function because of the asymptote at pi over 2. It physically will not go past pi over 2. So if I make this pi over 2, nope. Anything higher pi over 2, it won't work. If I did 1, actually, no, my bad. If I put pi over 3, it works. 4, 5, 6, and then pi doesn't work. But if I change my bounds to pi and t, now it's the second one. See that? It's the second one now. It's all about the bounds, guys. It's all about the bounds. And as for the case of pi over 4 and 3 pi over 4, since 3 pi over 4 is past pi over 2, it just won't work like that. But if I made it like 1.5, oh crap, now it works. So that's all I have to talk about today. I'll teach you sub another day. Bye.